And we are live. Hello. Oops. I was obviously looking through the slides, being a good, conscientious, prepared lecturer, and I forgot to reset it to the beginning. There we go. How are we all on this Friday afternoon? If you're in Sydney, it's not looking like a great Friday afternoon. It's windy and a little bit rainy outside. But, that's a good time to just be stuck inside learning about programming. So, today, this week, it's a big week, right? Because at the start of the week, we released the assignment. I've done 3 lectures. I've done 2 out of the 3 lectures this week. Just because I did an extra bonus one so that if people wanted, they could learn a little bit more about the assignment. That, I think I've now uploaded that everywhere. There was a little problem with the YouTube side of things, but I eventually got it uploaded to Echo 360 this morning, so people may have seen it already. What was I going to say? Yeah, so there's a lot of stuff happening in terms of the workload obviously increases in the course when the assignment comes out. But on top of that, we are starting to get to the point where you know enough about programming for me to start showing you some more complex and more difficult things. So if there is one lecture that opens people's minds to a new way of thinking about programming, it's today's. So today we're going to do something where we're not just thinking about, the bits and pieces of the programming, we're thinking about bits and pieces that reference other bits and pieces. So it's a little bit weird. It's about memory management and pointers. And this is going to flow on to us doing other, possibly deeper things with memory and stuff, which is something that not all programming languages do. Some programming languages just let the operating system deal with it. But if you don't have an understanding of how the computer memory works, it's harder to kind of have a good theoretical grasp on how you're actually using the computer. So at that detail level, I was talking about the Turing machine, I was talking about how there's the thinking part of the machine, and then there's the remembering part. We're going to get really kind of a little bit one step closer to the remembering part of the of the computer today. I'm sorry, Blake. Blake is too sleepy for memory. I got to admit, I have the same thing with the Friday afternoon lectures. I may have a chat with the powers that be at UNSW and suggest that Friday lectures ending at 6 p.m. might not be the best for our educational goals. But having said that, we're doing them now. We will be okay, because either way, this stuff is all recorded. So if it doesn't go into your brain the first time now, you can always watch it again later and see how you go. Okay, hey Jack. Jack is our mod for today, so he will be answering any questions that you have during the lecture while I am in full flight and talking about things. Okay, so let's look at what we were talking about in our last lecture, which was on Wednesday. We looked at functions and libraries. Now, we didn't really use any code with the libraries yet. I can't remember if today's example has got libraries in it. But in a way, you don't need me to do an example for libraries, because every single program we've done up until this point has had an include and has included the standard input-output library. So we've kind of already demoed it in a sense, but now you know where it comes from, and now you know that the standard input-output library is not the only one available, and you know now that that hash include line is not just a line that you had to be like, oh, we just have to do that. And we'll deal with it later. Now you know that it has a specific purpose, and you are going to be using it for adding code from other people, in a sense, into your code. We also looked at multi-dimensional arrays. This was quite important, I think, for a lot of people for if you've looked at the spec for the first assignment. If you haven't looked at the spec for the first assignment, I suggest you do so as soon as possible. Now, I'm not saying that you have to get stuck in and get coding or anything on it yet. You can take that as and when it makes sense to you. But I would say, at the minimum, read the questions. Because it can help, even if you only spend 20 minutes reading the questions. Your subconscious brain is going to be spinning those around in your head, and when you eventually sit down and say, okay, now I have time, I'm going to start working on the assignment, some of the solutions will just appear out of your brain, because your brain's actually just been spinning them around in the back of your head while you've been off doing other things in the meantime. So what I like to say is, if you're aware of what's going on, solving problems is much easier. Whereas if you just kind of surprise yourself, if you jump scare yourself with the assignment by not reading it, and then reading it 2 days before it's due and getting started, then it's much harder to just get into the mind frame of solving them. Yeah. Someone said it's magic and sleepy brain go brr, but it actually totally works. Willie's asking for chicken. Chicken is asleep on my bed, I think, at the moment, so she's so comfy there, she's probably not going to be turning up today, but we'll see. Sometimes she comes later. Okay, so multi-dimensional arrays was us putting arrays inside arrays, and so this is something that you've seen a couple of times now, where I've said we could put while loops inside while loops, we can put if statements inside if statements, and things like that. We start to learn that the C programming language, and is not alone in programming languages like this, that it can put code within code, which means you can get repeated depth of things inside themselves. So that's okay, it's all legal C, and it all runs. The only issue that we're always going to get is the more of this depth, this kind of Inception depth. I don't know if you know that movie. It's like they go into dreams, and they go into someone's dreams inside a dream, and it gets really, really complicated, right? And we can cause problems like that for ourselves in our programming if we start to put too many things inside each other. You may have noticed, I don't know how deep people have been going with your programming, but the style checker tries to remind you when there are problems like that. So if you get to four levels deep or more of indentation, the style checker will say, hey, are you sure about this? Because it could be a situation where maybe it makes sense sometimes, but at other times it definitely doesn't make sense, and you know that once you're that level of depth, you're going to get to a point where you can't remember where you are when you're reading it, and so that can sometimes be a problem. However, we do now have functions, and I think that Autumnal Blake is just saying that now that is actually something that we can definitely use, where if we have functions, we can actually say, all right, all of that depth, we're going to take some of that depth and put it separately in the function, and then we will have a certain amount of depth in the function, certain amount of depth in the main, and between those two, it would be confusing if they were all together. Because they're both separately, you can kind of think of it, you can think your way around it more easily. So yeah, just be careful if you're going to do something like 3D or 4D arrays, could be an issue. So let's look at what we're covering today. I'm going to go back over memory, and this is interesting, right? Because I've talked about memory a couple of times now, but it's all been building towards you having a good understanding of how memory works in your programs and in computers. And on top of that, getting you a good enough understanding so you can start to manipulate memory and you can start using memory. And this is a particular type of variable that exists in the C programming language, and it actually doesn't exist in a significant number of other programming languages, and that is this thing called a pointer. And so we're going to start using these things called pointers, and the interesting and sometimes incredibly powerful thing about pointers is that they are variables. They're a variable like an integer or a double is a variable, but they're designed in a very different way. So instead of them being used to store a value, they're actually used to store the location of another variable. So they actually store an address in memory that we know that another variable is at. Well, it's not always that we know another variable is at. Sometimes it's just another address somewhere. Walid was asking if the assignment was made with the intent to use pointers. It was not. So we've actually taught you, if you've had your tutorial this week, we've taught you everything you need for the assignment. You can start working on it now, knowing that you won't need anything. So some of the week 4 content was needed for that. This pointers could nearly be considered week 5 content in a sense that I wanted to introduce it in week 4 so that the tutorials and labs in week 5 can expand on it a little. This is by no means the last lecture that we're going to be using pointers. In fact, we're probably going to be using pointers for about 2/3 of the remaining lectures. So a lot of this stuff is going to come into play in a big way. funnily enough, we've been using memory addressing and pointers already. So this is the same thing I keep telling you. It's like, we've been using a lot of this stuff. But I had to hide some stuff from you in the beginning, because it's like, if I said, oh, we can directly address memory in week 1, I would get a record number of dropouts from my course. And I would have all these issues of people just going, I don't know why we needed to know that. This is way too full on. But now that we're in week 4 and we have this solid grounding, people are writing programs already, people are working with arrays. Some people, not everyone yet, because it's pretty fresh, are starting to use functions in their code as well. When you're at that point, you can then start to look at this stuff, which is like manipulating memory. But before we go too deep, let's do our quick recap of what we did previously, just to try to refresh these things in your memory. So, C standard libraries. These are the things like the standard input-output library, and we also showed the standard library and the math library, and there are other libraries that you can include when you're using C, and any C compiler will know how to find these libraries for you. So a lot of these are things that are just basically, they come along with C. You know, you don't have to install anything separate to be able to get them. You can just always include them. And these will give us a lot of the basic capabilities that that C can provide without you having to write the code for them. So something like printing to the terminal, something like reading input from the terminal. There's a lot of really finicky stuff that you would have to do if you had to do that manually, because you'd have to say, all right, what kind of terminal is this? And given what kind of terminal is it, what kind of information does it send, and then how do we grab that information from a program that's also running in the same terminal? It's really fiddly, right? And so we have ways of just sort of doing that in the background, and we as the programmers who are working on our programs just sort of accept that it works. So we have printf and scanf, but we're going to be adding more things that are going to be using more libraries as we go on. We also, make sure I'm not blocking the text, we also looked at multi-dimensional arrays. So, an array stores a collection of identical variables. And if that collection of identical variables happens to be other arrays, that's fine, C can handle that. So, we have this array here that has 3 elements in it, and each element in this array is another array that has 5 elements in it. And that way we can then start building a grid. Arrays in their notation are nice to us in that they will allow us to declare a 2-dimensional array just with 2 sets of square brackets like this. I don't have to declare each individual array that's going into this other array, so I don't have to declare 4 of these arrays to put into this array or anything like that. I can just do 2 sets of square brackets. And if you wanted more dimensions, yes, you could add more square brackets, but we're not going to be doing that in this course. We want to keep it to the point where it's like, you understand the idea that there's a more complex concept, but we're not going to make it unnecessarily extra complex. So we can have a grid like this, which is a 4x4 grid. You can still initialize it all as zeros. You can if you want to. I would have to check on this to be sure, but I'm pretty sure you can initialize all 16 values in one chain like this. But I'd have to try it, because I don't usually do that. Whenever I'm making a grid, I usually start it as zeros and then set it up with some other functions and stuff. The square brackets, as we knew before from arrays, but it's good to remember this. The square bracket is the symbol of the array. That doesn't mean it always does the same thing, it just means that it has something to do with arrays. So, when we declare an array, when we're creating it for the first time, the square brackets are going to tell us how big the array is. So we need to put numbers or constants in here to say this is how big the array is going to be. And then once the array has been created, if we're going to access the array, the square grid allows us to pick elements out of the array. So this is picking the 3rd element out of the array, which is an array, and then it goes deeper into the second set of arrays and says this is the first one out of the second one. So this is like going down 2 columns and then taking the first number there. And here's another access here, which is a different one, where we're going down 3 columns and taking the first number there. So once we get used to this, hopefully this won't be too hard, because the idea of going down rows then across columns is something that's reasonably intuitive, I hope. The only weirdness is that we're doing it in in programming directions where y often counts downwards. X counts across the same way from left to right that we would expect if we do a lot of maths, but then also 0, 0 is the first thing, and it's in the top left corner. Am I doing that in the top left? Yeah, okay. I have to mirror what I'm doing because I'm doing top right at the moment, but for you it's top left. Yeah. So these things, very useful to know about. Not just useful because they're in the assignment, they're in the assignment because they're useful. So a lot of this stuff is going to be the stuff we're going to be practicing, and when you get to a certain point of understanding these and you're able to complete some parts of the assignment at least, then we're happy to say, all right, this person's been through hell and back. We've made them do all these kinds of weird stuff with arrays. We think that they'll be able to handle anything with arrays in the future. And that doesn't mean that someone can't make an array that will confuse you, because that's still quite possible to make. I mean, I could just make a 5-dimensional array and all our heads will explode. But if you've done everything in the assignment, you should be able to handle most anything that's going to happen with normal arrays and multi-dimensional arrays. So, let us think now about memory in our computer and how it actually works. So I'm going to start by setting up an analogy of how memory works in a computer and talking about how we can work with that, and then drilling down into the details about how we're actually going to do that in programs with C. So the way I like to talk about this is memory is like a neighborhood, in that every house in a neighborhood, so let's say we've got streets, or we've got a grid of streets or something like that, and we can even nearly think of it as one street, just one really long street. Let's go for Anzac Parade. If you know Anzac Parade, I mean, if you've been to UNSW in Sydney, then you've most likely been on Anzac Parade, which is the big street that goes past UNSW. It starts several kilometers away, nearly at where the city is in Sydney, so it links up to Oxford Street, and it goes all the way down to, I think, La Perouse, I think, at the very, very bottom of the peninsula, the eastern, sort of eastern Sydney Peninsula kind of thing. So it's a big long street, and it has a bunch of numbers going all the way down it, which means that every location that can be on Anzac Parade, we can identify it because it has a unique address. So we could say, I don't know, 100 Anzac Parade. I don't know if it restarts its numbers in different suburbs. I know that very, very long streets like that will do it. So maybe it's not 100% unique. But either way, I do know that I can find every single location, every single house or shop or everything on Anzac Parade using a unique address. And our computers will do that as well. Every piece of memory in our computer is separated into bytes. So we've worked with bits and bytes before, right? A byte is 8 bits, and so the byte is considered, at the moment, so this is always going to be based on current computing. At the moment, the byte is considered the smallest single piece of memory that we use. So we have all these tiny little 8-bit chunks of memory, and each one of them has a different address. So each one of them has a number where we can access it from. And you kind of know this because you've seen this already in arrays, in that we said, oh, okay, we've got a big chunk of memory, and we're accessing it by an index number. With arrays, it's slightly different because every chunk of the array is exactly the size of a variable. So there's 0 is the size of a variable, 1 is the size of a variable, 2. And if we're doing something like integers, those are 32-bit sizes of variables, which means that's 4 pieces of memory. But either way, the concept of it is very, very similar, where we have a whole bunch of things, and then we use numbers to find individual parts of that big chunk of memory. So when we're looking at the memory in the entire computer, we have all these 8-bit chunks, all these single bytes, and each one of them has a unique numbered address that we can use to find it. Just checking chat. Oh, I think Jack's on top of chat there. Jack saying, yeah, it finishes somewhere around Malabar or La Perouse. Yeah. Yeah, so if we have that, then we know that theoretically everything that we put in memory has a number attached to it, and that number is the address that says where it is. So in the same way that I could say, if I say, I don't know, 250 Anzac Parade, and I say, all right, everyone, tomorrow at this time, we're all going to turn up at 250 Anzac Parade, so long as it doesn't reset its numbers in different suburbs, which I think it might. If it didn't, we'd all end up in the same place. I mean, like, obviously a lot of people would need to travel a very long way and probably wouldn't get there in one day, but a lot of us would be able to find the same place. And memory's like that as well. Once we put something in memory, it has a location, and we can use the address of that piece of memory to find something like a variable. We're going to start drawing a lot more pictures in this, like, as we go into the second half of the course. I mean, we're not really in the second half of the course yet, but this is something we're going to use more in the second half of the course. If we were to draw a picture, we could have somewhere in memory, there were these 8-bit blocks of memory, and each one of them would have an address, right? So we've got here, I'm just making these up, 105, 106, 107, but it really is like that, where every address for memory is an integer. Right, so it's just a number, and it's a whole number because we're not going to do any partial addressing. We're never going to address 105 and a half and get a piece of memory that's halfway through this. We're always just going to have them in their chunks. But if I know the address of a variable, so if I can find the address of a variable somehow, and I am going to show you how, but somehow I could find the address of a variable, it means I could find that variable without even needing to know the name of the variable or what it's used for or anything like that. I would still have access to that variable. So if I say the same thing, like 250 Anzac Parade, and I start handing out bits of paper to people saying, okay, 250 Anzac Parade, you remember where that is. People would be like, yeah, I can remember where that is. 250 Anzac Parade, I've got my piece of paper. That's actually the variables that we're going to be using. We're going to be able to have those variables that tell us where something is. So continuing this, I do like this analogy because I think pointers and memory can get real abstract really quickly, and the more abstract and less grounded in reality a concept is, the less it's going to just go into anyone's heads. So a variable is a house. And the house exists at an address somewhere, and that is where it is in memory. So every time we've been making variables, right? Anytime we've said int something, or int array something, or double something, our computer has gone, all right, you want one of these? That's fine. I will reserve a piece of memory of the right size for you. And it will actually know where the addresses are for each of these things. We've been using something that sort of uses those addresses, but not precisely uses them. Whenever we use a variable name, the compiled version of the program that is currently running in memory will go, okay, that variable name is this memory address, and we'll go to that memory address and we'll let you change things and stuff like that. So that is kind of the house. The house is where the variable sits in memory. When we have our 64-bit systems, which I would say is probably 99% of the computers you're using at the moment, that means we have 2 to the 64 possible memory locations, and each one of those memory locations can store 8 bits or 1 byte of memory, which means that we have what we would think of as an address space to be able to look at a very, very large piece of memory. I can't remember how much memory 2 to the 64 bytes of memory is, but I think, if I remember correctly, it is way beyond what we need at the moment. So, has everyone been to Wolfram Alpha at any point? This is like this maths website that basically you can type in nearly any equation and it will explain it to you. Oh wow, 2 to the 64 bytes. It's actually here as an autocomplete. So 2 to the 64 bytes, this is the maximum possible amount of memory that we could address, is 18.45 exabytes. So exabytes are things that we haven't even heard of in modern computing yet. I mean, like, some people may have heard of it, but in terms of just like consumer grade computing, we're at terabytes but we haven't even reached exabytes yet, which means our current capability for addressing memory is future-proofed against against our computers getting to a certain point where, where they may actually need that. So I need to show you something interesting. This is a historical thing. It's not super important, but this is like what we used to be working with. So when we were initially working with memory, when all of our computers were 32-bit computers, and this wasn't even that long ago. This was I think even into the first decade of this century, the 2000s. So I don't know when we crossed over entirely. We were still sometimes using 32 gigabyte machines, which means we had this ceiling of 4 gigabytes of memory. And once we got beyond this 4.295 gigabytes of memory, we couldn't actually use any more of the memory. We couldn't address it because we only had 32-bit numbers for addressing memory. So things got super awkward, which is why we have 64-bit systems now. It was actually even worse than that. It used to be like 2 gigabytes were reserved for the operating system, so any program you ran had a 2 gigabyte limit, which nowadays makes no sense to us because I think a lot of our computers now are running 16 or 32 gigabytes of memory. So if we were on the old system with just this many possible addresses, we wouldn't even be able to use all of our memory. People had to do these funny tricks to actually get it to work. I won't bother talking about that. It's like too complex. But yeah. So this is the system we're working in. We have our possible 2 to 64 bytes of memory. Obviously, we don't physically have that much on most of our computers, unless someone's got some, like, I don't know, Amazon cloud services massive computer that's doing multiple things. Even that's usually broken up into separate computers. But anyway, this is the address system that we're using, 64-bit integer that stores an address. So a little bit different from the integers we've been using, the 32 bits, but the 64 means we can easily address all of the memory that we might want to use. So, what are people talking about? Windows XP and stuff like that. Yeah, totally. I think Windows XP was the last 32-bit Windows. I think that Windows 2000, once that came out, was a 64-bit. But don't quote me on that. I can't remember exactly. I know Windows isn't the only operating system, right? There's plenty others. Like we're using a Linux variant in VLab and other things as well. Oh, Taotao's saying Windows 7 has a 32-bit option. So there are still, I guess, backwards compatible versions of Windows. Anyway, let's continue. So, I want to introduce to you a new variable type. So this is actually the first new variable type we've introduced. I think everyone was expecting me to introduce characters next. So we had two different types of numbers. We had whole numbers and we had fractional numbers, as in our doubles, our floating point numbers. And everyone was expecting, well, he's going to do letters next, right? And then we can do letters and words and stuff. And we are going to get there. But what I want to do is to teach you more about the theoretical nature of the computer and how it works. Because letters and numbers, it's not that much different. They're just storing information. But pointers are storing something different. They're not just storing a letter or a number or something like that. They are storing the location of another variable. And so things get a little bit weird here because now we have variables whose existence is kind of predicated on the locations of other variables. So very, very interesting kind of things like this. So most of the time when we create pointers, we create them specifically so that we know where other variables are. We're using them as a way of us, in a sense, writing down the address of another location. So when we write down the address of another location, it means we can use it in different ways than we were doing it before. So, as I was saying, this is the same analogy. If the variable somewhere is a house, a pointer that aims at that variable is a pointer that stores the memory address of another variable. So a lot of the time, whenever we're talking about pointers, we think about where is this pointer aiming? Because it's not really that important, the variable of the pointer itself. What's important is what it gives you access to. So in the same way that I could give you a piece of paper that has an address on it, the piece of paper is not as super valuable as the address on it and what it leads you to. That's the thing that has value. So pointers are like that. They are variables, They sit in memory just like any other variable, but the important thing about them is not necessarily that they're, like an integer is important to us because it's keeping track of a number that we're using for something. But the pointer's not keeping track of the number itself, it's keeping track of where something else is. So this is why this gets a little complicated at this point, because we start to think about not having variables just as values, but variables as locations of other variables. So now we're getting down to the actual code of how this works. Now I was talking before about arrays and the square brackets being the symbol of the array. And that meant that anytime you saw square brackets, the code was either going to create an array or access an array. Pointers are similar, but they have the asterisk, the star. The star says that if a star, and I mean, you've got to be careful with this because this is the multiplication symbol as well, but if the star is attached to a variable, then it means it has something to do with pointers. So either we're creating a pointer or we're accessing a pointer in some way. I'll tell you about the different ways we're going to access pointers. So if we declare a variable as a pointer like this one here, there's a couple of things that we're always going to be doing. We can't declare a pointer without saying what kind of variable it aims at. And the reason why we have to do what variable it aims at is because the pointers need to know how big the house is that they're aimed at. Because if we go and look at what a pointer is aimed at, we need to know whether we're reading 32 bits of it and converting it into an integer, or whether we're reading 64 bits of it and converting it into a floating point double, right? So every pointer always has the type, and this is the type of variable it aims at. And then, of course, it's going to have a name, but it has this star here that says, okay, we are creating a pointer, in the same way that when we were creating an array, we would have the square brackets here to say, yeah, okay, it's not just a normal integer, it's an integer array. And this one here, it is not just a normal integer, it's a pointer to an integer. So the pointer is its own kind of thing, and the star says this thing is going to point at an integer. Now, looking at a symbol that you have already seen, but before I just said, look, we're just going to gloss over this because we don't yet have the knowledge necessary to understand exactly what's going on with this AND symbol. Now you do. Now you can understand what the AND symbol does. What it does is it basically does a lookup on a variable and finds out where it is. So this is like typing in UNSW into something like a mapping service like a Google Maps or something like that. When you type in UNSW, it'll tell you the address that UNSW is at. UNSW is really confusing though, because it doesn't have a proper address. The entire university just says, I think it's like University of New South Wales, Sydney 2052. So it doesn't even have a street or a street number or anything like that, because it's so big. It's basically an entire suburb on its own. That was an interesting question there. Lorenzo's asking, what happens if you do integer IP, so without the star, so you don't make a pointer, and then you set it as the address? The value in that integer would then be the value of the address. So it would be some weird number that is one of the 16 gigabytes worth of memory. It'll be wherever that piece of memory actually was. I'll show you this in a second, actually. We'll actually show you what these addresses look like. It's also a really good question from Blake there, which is, why can't scanf just use a normal variable? The reason why scanf can't use a normal variable is because scanf needs to know where to put information. If we put a variable into something like scanf, what happens when we put a variable into a function? When we put a variable into a function, what goes in is whatever number the variable was storing. So if I have an integer that is currently equal to 5, and I put it into a function, 5 goes into the function. And that doesn't give us access to writing information into the variable. Whereas, if I say this is the location of memory where this variable sits, please write information into this location, that can be done, because it's like, all right, yeah, I know where that memory location is. I can write the ones and zeros into that memory location. But if I give a variable to a function without the AND, all it does is it gives it a number to the to the function. But I'm going to talk more about functions in a second, so let's keep going, right? So and is the address of the variable, and the use for scanf is more subtle of why it needed to do that, because if we just gave it a variable, it wouldn't be able to write anything to that variable. It actually needed to know the address of the variable to be able to write information to it. We're going to be doing stuff like that even today. Oh, sorry, I was blocking up the title there. Okay, so pointers have types. Different pointers that are going to point at different variables have different types. So if I have an integer here and a double there, if I want to point at an integer, I should have an integer pointer. And if I want to point at a double, I'll have a double pointer. So I've just got this integer pointer, double pointer. I've just sort of shorthanded everything here because this example doesn't have any particular meaning. When I think I've got a pointers demo piece of code in the lecture code for today, so it'll be in the lecture section of the website, but also in the live code for today as well. The other thing that's going to happen, Blake, point at a pointer. Wait for it. I will talk about that. The other thing that that we need to do is we need to think about initializing pointers. It's a variable, right? So there's a few things we think about that's always going to happen with variables. We need to know how to create them. We need to know how to name them. We need to know how to access them. But we also need to know, if we're going to create them, how we're going to initialize them. And most of the time, pointers are going to be initialized like this, where it's like, make a pointer and just kind of like bind it to a variable immediately and go, this pointer gives us access to this variable, you know. And you might actually at this point be asking, why would we bother doing that when we've got the variables? I will show you things that we can do with pointers that we can't do with normal variables in a second. But sometimes when we're going to initialize a variable, like we've done this before with other variables where we've initialized them and said, I don't really have a starting value for this. So for the moment, since I don't have a starting value, I need some kind of 0 or something, or some kind of like non-value. And this is where we get the hash define called null. It's in the standard library that we'll be using a lot with pointers. I think it's also in standard IO. It's in most of the libraries that you can include in C. And this hash define says not pointing at anything. And this is going to come in very handy for us because a lot of the time we're going to have pointers that we say are specifically not pointing at anything. Because if we gave it any other value, that would be somewhere in the memory on my computer. So I'm just pointing at my computer there that you can't quite see. So somewhere in my computer here is some memory. But if we give pointers values and we start using them and they're not pointed at specific pieces of memory that we want to use, then they're very dangerous, which is why we use null. So we want to say that a pointer is specifically not aimed at anything, we'll initialize it to null. Lorenzo's asking if null is 0 or not. I think on some operating systems, majority of operating systems, null is actually 0, but it's actually going to depend on your implementation. So it's the kind of thing where it's like, you asked a giant question, I have to give you the simple answer, because we don't have time to go into the super, super giant question. So I've said, how do we create them? How do we initialize them? And the edge case of initializing them as null if we have to. And now we have to think about, how do we use them? So how do we access things? One of the most important things we're ever going to want to do is say, this pointer is aimed at a variable. Can we get the value of the variable that this pointer is aimed at? So there's two weird things here. There's two concepts happening here. The pointer stores the address of another variable. So if I say, what is the value of the pointer? It's going to be some number that sits somewhere on our computer. So it's going to be some 64-bit integer that is, pointing at my computer again, literally a physical position somewhere on the RAM chips on my computer. So it'll be like, yeah, go to this position, right? I mean, obviously it's not that exact. It's going to be translated by my operating system to be like, okay, you used this number, which is the way I told you things, and then I go into the computer and I translate that and I find that actual piece of memory. But it is actually going to some memory location somewhere. So that is the value that is stored in the pointer. But a lot of the time, we're not really using that as a value. We're not using that as a number. We're using that as a way to find another variable. So somewhere in memory, is the value of my pointer. Somewhere else in memory is where my pointer is aiming at. And so, if I want to access the variable that my pointer is aiming at, I use the star again. Star being the symbol of the pointer. So, when I create the pointer, the star says this variable here is a pointer. Then, when I use the star again after I have created the pointer, so now that I'm using the pointer after I've created it, this thing will actually follow the pointer. So it'll go to the pointer, it'll read the pointer, and it'll say, what address are you aimed at? And it'll go to that other address, and it'll say, what's there? So it's like, here, I created a pointer that was aiming at I. The value stored in IP, the integer pointer that I've got here, is some number. I don't even know what it is, right? Because it just depends where in memory my program has been created. So it has a memory address somewhere stored here. And so if I look at the memory address here, so I could print out the memory address as well as the value. The star takes me further, takes me into the value. So I like to think of the star as you reading the address on the piece of paper and then going to whatever, like 250 Anzac Parade. I don't know where that is. Don't necessarily just randomly go there, but yeah, you read the piece of paper and you go there. So you're not worried about the numbers that are on the piece of paper. You're worried about what's at the end. So the star here says, follow this pointer to its destination, and then look at the variable there. We call it dereferencing. That's a word that you're probably going to get. You're going to hear a bit more once you go deeper into computer science. Dereferencing a pointer says this pointer is a reference to something else. Dereference means I go all the way to that destination and I try to figure out what's there. It's probably not a bad time for us to see this working. We're in lecture 8, aren't we? Yes. And I've got my pointers C file here. So this has some of the stuff that I've been talking about already, but some other stuff that I'm going to talk about later. So if we've only got this much of it here, let me just comment out these extra bits that I will show you in a moment. Basically, I've made just one program that has everything that's in the slides, all the code that's in the slides. But let's just look at this one piece here. So I'm going to save this, compile it, I'm going to call this pointer demo. Should remind you that, you know, like even little things like this that we haven't been doing that much of, a lot of this stuff is just options. You have your file name, you always need to have the file name, but your output, whatever program you want to name, you can name it whatever you want. Okay, so compile that, and I run pointer demo, and it says this number 0x7FFDBBE1C960 is the address of I, which has the value 100. Okay, so let's have a look at what this was. The %P allows us to look at the pointer as if it is a memory address, and it's a specific numbering system. So I don't know if people have heard of this numbering system before, but it's called hexadecimal. Hexadecimal is a numbering system that has 16 possible values for each digit. So in binary, our possible values for each digit are 0 and 1. In decimal, which is the thing that we're used to, the possible values of a single digit are 0 through 9. In hexadecimal, there are 16 possible values. It goes from 0 through to F. So it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So 16 possible values for each digit. And you can be wondering a little bit like, why are we doing that? Why are we using this other different numbering system? And the reason why we're doing, well, the reason why hexadecimal exists is it translates from binary really cleanly, because binary works in 2s. So if we have a, is it a 4-bit number? no, it's a 5-bit number, I think, is exactly has exactly 16 possibilities. And so this works really well because the choices of digits is exactly divisible. Not divisible, it's actually a square of 2. So that's just a little bit of trivia. So a lot of the times, and you'll see this, it's really funny, you see these numbers pop up in computing a lot of times. Like, why do people use 1024 instead of 1000 when they're talking about gigabytes and gigabits and stuff like that? It's always 1024. It's because 1024 is actually a multiple of 2. And so everything in computers ends up being some kind of multiple of 2 because of the binary nature of the computer underneath it all. Sorry, it was 4-bit, Blake was saying, yeah. I don't know how I ended up with 5 bits there, because it should be 1, 2, 4, and 8. And that would, yeah, so the 4 bits is 16, yeah. And Lorenzo's asking, good question, why does this start with a 0x? And they all start with a 0x. The 0x is actually a symbol that just says this next bit of number is going to be hexadecimal. So it's just something that, in terms of, like a convention amongst computing people, that when we see 0x, it means the next thing is going to be a hexadecimal number. So this full-on, highly detailed number is in VLab, somewhere in CSE, an actual location for memory. And this is the thing that when we created I in our program, and I said, run this program now, my operating system says, okay, I will give you this piece of memory, and drilling down into the detail of this piece of memory, this is where I is. And if you want to know where I is, you can do AND of I, and I will give you this number. And this number is a way of accessing memory, because this is the exact location in memory somewhere where that integer has been placed. So then we make this pointer using a type, because it's an integer, and the star attached to the variable name to say that this is going to be a pointer, and it says, okay, this will store, IP will now store this number. So IP is storing that number here, and we can see that because we said, all right, print it out as a pointer, which means it'll be a hexadecimal 64-bit number in our case, and it says, okay, this is the address. And then we used the star, and the star says, I'm not interested in the address anymore. I'm interested in following that address to whatever variable this pointer is aimed at, and tell me the value of that that variable. And so this time where I do star IP and I say do that as an integer, star IP goes here and says, okay, what address were you storing? Oh, I was storing the location of I. And so this then here can take us to I and says, I was storing the number 100. And so in the 32 bits of memory that this pointer is aimed at, the 100 was there, and that's how we get the value there. So we're starting to get the idea that when we use pointers, we're using the locations of things, and then we can go to those locations. Someone was asking there, Shrika was asking, does the location change every time we run the code? That's an interesting question. Let's run it again. It is not the same. So some of it is the same up to here. So that's just the large section of memory that we're in, but this is very different. So what's happened now is the next time I've run this program, I've said to my computer, I would like to run the pointer demo program. And my computer says, sure, you can run the pointer demo program. Here's enough memory to run that program. And obviously, I had enough memory somewhere near this location previously, and this time it's given me a different piece of memory somewhere in the VLab computers, because someone else must be using other parts of VLab at the moment. So that memory is getting shuffled around between different people and stuff like that. So my program is still happy to run, but it's been given a different piece of memory somewhere else, which means the location of my variable is different from where it was previously. So yeah. Cool stuff like that going on there. I don't want to go too deep into this because we're going to do a demo later as well. But this code is, of course, as usual, here for you to play around with. I have more stuff that I want to talk about in the slides. So what we've got so far, we can create them, we can initialize them, and now we can use them to find the variable that they're aimed at and get the value out of them. We can also just print out the raw memory address, but as you can see from the raw memory address, we're not super interested in raw memory addresses. They're just complicated numbers that we don't have any context for, because we don't really know where we are in memory. So the things that are going to become important to us are actually using pointers with the bits of programs that we've been writing so far. So we want to think about what happens if we give a pointer to a function instead of giving a variable to a function. Now, in order to think about this, we need to think a little bit more carefully about exactly what happens when a function runs. So when a function runs, we have the inputs passed in, what is called passed in by value. Different programming languages actually do this in different ways, so this can get super confusing the more programming languages you learn. But when we're just thinking about C, and we're only going to be thinking about C in this subject, function inputs are passed in by value, which means you do not get the variable when you pass a function into a value. When you pass a variable into a function, you do not get access to that variable. What you get is whatever value was stored in that variable is copied into your function, and then the function makes its own variable. That is the same type as the variable. They have to be the same type for the function to work, but the function makes its own variable and then works with it. So the interesting thing then is, if I have a copy of the variable, it means I can't access the variable. But what if I had a copy of the address of something? So this is really interesting, right? Because if I say the number 100 and I give you the number 100, you can't do anything with it, because you don't have my number 100. But if I tell you I stored the number that I want you to change at, I'm just using the same thing again, at 250 Anzac Parade, then no matter who I give that to, you will all be able to find this 250 Anzac Parade and change whatever's there. So I think I need some pictures here to help you understand exactly how this is working, right? So functions pass variables in by value. So I've got a variable in my main, and I call the function. So the function has its own memory space. The main has its own memory space. So when the function runs, it copies the value of this variable and has its own variable here. So it can do any changes it wants to this variable, but it has no access to this variable. So the stuff in our main doesn't get changed. Joseph was asking, the pointer is by reference. Yes, that's exactly the two different ways it's talked about. So it's either talked about by value or by reference. So if we give a pointer to a function, we're giving it by reference. So this is what happens in a normal function. I give a variable to the function. If the function makes changes to the variable and then goes back to the main, nothing happens. If I want to then change this or other variables, I could return a value in the function, and then it would have to then store that value in something in the main. But this means that we have a variable and we have a copy of the variable, which means we've copied the value, but we have no, the function has no way of accessing this variable here. However, we can do things in a different way. So pointers are also passed in by value. They're also a variable that gets passed in by value. They do not break the rules of the function. So the function's rules are, if you give me anything, I will take the value of the thing, but I will not have access to the original variable. But let's think about this. If I have a variable, I have created a pointer to that variable. This thing knows the address of that variable. Instead of passing the variable into the function, I pass the pointer to the variable into the function. I now have a copy of the pointer here, so it's not the same pointer. It's a new pointer, but it's storing the same value as this pointer, and so both of them have the address of this variable. This function now knows exactly where this variable is in memory and what type it is. It can now use it. So I can now go in, I can follow that pointer to its location, and I can actually make changes to it and things. So the interesting thing now is I've set up a situation where I have functions that can access variables in my main and make changes to them. So you can do this kind of thing with pointers where you go, okay, here's my status of something in particular, and the function runs, and if it needs to change the status of that thing, it was given access to it by a pointer. So it's kind of handy like that. The way this little bit of code here sort of illustrates how this might work. So we know now, if we give a variable to a function, it will be copied into that function, but we will never have access to the initial variable when the function's running. The pointer passed into a function will give us access to whatever it was that the original pointer was aiming at, because a copy of an address still gets you to the same place. So two functions here that are both trying to add 1 to the number n. This increment int will not have any effect on our program because we give it an integer n, but what we're doing is we're saying, here, have a copy of our integer, and then you add 1 here inside your curly brackets to the integer that has been created inside the function, and then once the curly brackets end, the integer that was created inside the function disappears, because whatever goes on inside the curly braces stays inside the curly braces. So everything that was created, this int was actually created inside the curly braces in a sense. It's created inside the function, so it will disappear when the function ends. Here we have a pointer, and the pointer is going to do stuff. The pointer itself is going to disappear when the curly brackets get hit. So the pointer still only exists as long as this function is running. But if we do star on the pointer, what this does is it says go to whatever memory location this pointer was aimed at. And so this says go there to that location and assign it the value of go to that location, read its value, and add 1 to it. So what this is going to do is if we have an integer in our main and we create a pointer to it, and then we give that pointer to a function, that's like saying to the function, here, I have a secret treasure, and here's the treasure map, and I want you to add 1 to my secret treasure. And you just go, okay, because I've got the treasure map, I know where your secret treasure is, I can add 1 to it, and then it goes up in value. So you can nearly think of pointers as being like, you know those like old pirate treasure maps that have like, go here, and then when you get there, you then read the next treasure map and you can go on from there, that kind of thing. So pointers are like that, where they say, okay, here's a location of something, and then you can do something once you get there. Yeah, so people are working out that kind of thing there in chat, and people are saying of like, can we do star n plus plus? Yes. So star n is just going to give you access to the variable as if it was a variable. So if this is an integer pointer, which it is, and you do star on it here, you can use it just like an integer. So you can change it, you can increment it, you can take its value and use it elsewhere, that kind of thing. And also, Saya Schrödinger is also saying that like, so the pointer kind of bypasses this curly brackets thing in a sense, where the rules of the curly brackets was everything goes on in there stays in there, but the pointer is actually not necessarily working within the curly brackets. The pointer allows it to work on someone else's set of curly brackets, so long as it's been given access to something. It doesn't actually necessarily break the rules, it's just been given access to something else, because these curly brackets still are in control of their own domain. They're a master of their own function memory space, in a sense, where the pointer will still be destroyed once it hits this curly bracket here. I will later teach you about things that really, really do break the curly brackets rule and give us all this extra power to do things. But obviously, power needs to come in steps for you to be able to understand it and use it. Okay, so check out this function now. On Wednesday, I was looking at the tourist and saying, oh, this would be really cool if I had a function that could move the tourist. But there was no way I could do that, because the functions as we were thinking about it previously could only ever change one value. And if I had two coordinates, I could never change a value. I could never change either one of them if I wanted to, because any function that I had would only have one output. So I couldn't say, oh, change the row coordinate or change the column coordinate. But now with pointers, I can. So here's a function that's really, really simple, but we didn't actually have the capability to do this before. So I have two integers. So here I've been given the pointers to the integers n and m, and I want to swap them. Let me, I'll show you just this really, really super basic integer swapping thing. So I've got one integer here, one integer here. Both of these are 32 bits of memory. And so say that this one's 6 and this one's 8. If in a computer I want to swap these two values so that this variable, let's call this variable m, and this variable n. If I want to swap these two values, then there's no way I can swap these two values without using another piece of memory, because I need to save one of these somewhere. So let's create another integer here, and I'm going to call this one temp, because it is a temporary one. So what I could do is, first of all, I go, okay, let's copy m into temp. Oh wait, copy. We copy m into temp. So this goes in here, and then we copy n over m, which is going to replace that with the value that was in n. And then we copy from the temp into the n here, which replaces the value in the n with the value that I was storing in the temporary one. There. And so just with that moving around, we can then swap the values that are in two variables. But there's no way that we would ever be able to swap the values in two variables without this temporary space somewhere to store one of them while I was moving the other. So you get this, just this simple thing like this, and in a function we were never able to do this because we never had access to two variables at once. We could copy their values in, but we could never give two different values back out of a normal function. But instead now with pointers, we can get access to the memory locations for those two variables, and I can make a temporary one here. So I've got my temporary piece of memory, this integer here, and I've said the temporary gets a copy of n. Oh, it's actually different from what I did. It's the opposite, but you know, that's the same thing. So temporary gets a copy of n. Then because I've saved n there, I can replace n with m, and then I replace m with the temporary. So it's just this same thing that I just did there. You can use this to swap the locations of two variables. But the interesting thing about this is if on Wednesday I had asked you, now that you know about functions and these kinds of things, I asked you to write a function that could swap the values of two variables, it would have been impossible. We didn't actually have enough access to memory to be able to give back two values from functions. So this is really interesting now. So we start to see that pointers are giving us slightly more capability than we had previously. So more stuff happening. Pointers and arrays. Now, this is a really interesting thing, and this is the question that we had earlier. I can't remember who asked it. But someone was asking if we can put an array into a function and change the values of things in an array. And if I say to you, what are the rules of a function, you would say that any input that we put into a function, any variable we put into a function will be a copy of the variable, so you won't be able to change stuff that's in an array. But this is where the interesting thing happens with arrays. An array variable, so if I use the name of an array here, so not accessing an individual element of the array, I'm trying to access the whole array. The array variable is actually the memory address of the start of the array. So the interesting thing about it is if I use the array by name without accessing an individual element, just by the name of the array, I'm actually giving the function a pointer to the start of the memory of the array. The array name itself is the memory address of the start of the array. So this is really interesting, because what we've actually been doing, if you've been doing stuff with arrays so far, is you've actually been giving pointers to a function without knowing it, because the array name itself is a pointer. And an interesting thing here is if we try to get the address of the first element of the array, so the first element at index 0 of the array, and we say, what is the address of that element, that is exactly the same address as just using the name of the array on its own. So, very, very interesting thing then with arrays is when you pass an array into a function, it's not going to copy the whole array into the function. It's going to copy the address of the array into the function, and then you'll be able to use the array, and any changes you make to an array in a function are going to go back through memory to the array itself. So the array that was maybe declared in your main or in another function or something like that, and it's going to make changes to that one. So I love this meme. I'm gonna get out of the way. Get out of the way of the Spider-Mans. Spider-Men? Spider-Mans. Ooh, interesting. Anyway. Pointers are variables. Yes. So, Hussein's asking, arrays are global? Arrays are not global. Arrays can get passed around as pointers, but they will still always follow the rules of the curly brackets that they're in. So the array can't escape the curly brackets that it's in. It's just very, very easy to pass pointers to arrays around because the arrays themselves are pointers to themselves in a sense, right? So there's a subtle difference, right? We don't use globals at all in this course, and in general, we try not to use globals because they tend to break code in ways that we're not expecting to happen, so they're super, super dangerous. Anyway, this was another question earlier, which I laughed at because it was like, this is something that we've got to worry about. Pointers are variables, yes. Pointers can point at variables. And it's like, oh no, does this mean that we can aim a pointer at another pointer? Because we can. And this breaks the entire analogy that I was saying about the address. It's like saying, go to this address, and then in the house at this address is the address of another house. And then go to that one, and then in that house there's an address of another house. And if you keep following that through, you will eventually arrive at a destination of some sorts. So, learning pointers, learning how to address memory, learning how to access another variable through a pointer is hard enough as it is. Once we start using pointers to pointers, things get really messy. So we're not going to do that at all in 1511. I'm going to point out that they exist, and there are uses for them. Like, I've definitely used them before. But for the moment, we need to get our grasp on the idea that we're already getting to the point where we're using variables that we don't necessarily know about. We only know where they are, and we know that somewhere else we were given this location, right? So we want to be more careful with that, and we're just going to be like, hey, well, we're not going to do pointers to pointers just yet. You will eventually find uses for them, but that'll be if you're going to continue on and do later courses. You'll see them. Okay, so I'm going to wrap it up there and take a break. I've got a little bit of trivia here for the fun of it, about Slide, and Slide being based on old kind of mid-1980s arcade games and stuff like that. So computers and games have been very, very strongly linked for, nearly the entirety of their existence. So I don't know what it was, but it seems to be everyone who worked on computers in the beginning was like, hey, you could play games on these things. And then now it's like, yeah, of course you can play games on these things. Some of these are made only for gaming, and we happen to use them for other things as well. So yeah, a little bit of detail here about where you could think of something that is relatively simple that you're going to do in Slide, which is like something, it's a program you're going to write in your first kind of 2 months. Some people, it's going to be your first 2 months of programming ever, and you're going to be able to create something which is really actually tapping into this deep history of how computers and games kind of work together. Okay, so we're going to have a break. It is now 5:07, so we will come back at 12 past 5, and we're going to make a program that's going to use both pointers and functions. Alright, so Levi's asking when's break till? 5:12. Actually, it's 5:08 on my clock now, so it'll be 5:13 that we come back. Alrighty, we're back. I just turned my little air conditioner on, so hopefully there's not too much background noise. So yeah, a whole lot of interesting chat in in the break time there. People are asking about a lot of different little things, like if we had the address of an array in memory, could we just jump 32 bits further along and get another integer? Like if it was an integer array, and could we just jump another 32 bits and get another one? Yes, you can. That is exactly what the indexing thing is doing. So when we index, basically you take the index number and you multiply it by the size of the variable in it. So for an integer, it's going to be 4 bytes for each integer. So you take the 0, you multiply that by 4, and you add, or the 0, or whatever index you're using, you're multiplying it by 4, adding it to the address of the array itself, and it's jumping across exactly far enough in memory to get that next variable. So under the hood, all that stuff is actually happening. And if you really wanted to, if you want to make life hell for yourself, you can address, you can start modifying pointers, the value of pointers, to find different variables. I don't suggest doing this at all, ever, like ever, even when you get into professional programming, because the chances of getting things right are very, very low. The chances of getting things wrong, very, very high, because you have all these custom numbers in there for moving around between variables, and then you would end up with this issue where you can't find stuff. Yeah, so there's like funny things like that. Okay, let's go into our demo where we're going to make a program that's going to kind of shuffle a deck of cards. It's not really going to shuffle it very well because I'm just doing a simple program to do this. But what we're going to do is we're going to take some numbers as inputs. So at the beginning, our user is basically going to tell us how many cards are in their deck. We're not necessarily going to do like a 52 card deck. We're just going to do something simple with a few numbers. And then what we're going to do is we're going to use that swap function pointing into the array of numbers and just swap a few things around. And then we'll print them back out, and they should be a little bit jumbled up from what they were before. This is not a genuine random algorithm, although for a challenge, which I don't think I've even put in the slides, for a challenge, you could try doing this with a random algorithm instead of what I'm doing here, which is just swapping a few things. So we're going to use functions, we're going to separate the functions, and we're also going to use pointers to get access to parts of our code and things like that. So it's a slightly contrived example. It jumps through a few hoops just to show examples of things, but hopefully it'll be interesting anyway. So, how are we going to split up our functionality? So I've said a few things that we're going to do. So, we want to read the input as integers, so we can have a function that does that. We want a function that swaps two numbers. I've already shown you... Wait. A function that swaps two numbers, so we're going to like pretty much copy-paste this function and use it. We want a function that doesn't just swap two numbers, but goes through a list of numbers and swaps multiple of them. So that way we get our kind of shuffling idea. If I had a deck of cards and I was shuffling them, for example. And then we want a function that prints out the numbers. So that should be the simplest function, is one that's just going to loop through an array and print things out. But it may have some complications. So let's look at the first... I think the first two of these that we'll do is first we'll read in the inputs and then we'll print out the output. So the first thing we're going to do is write a function that reads inputs into an array. So we're going to have an array that we're given. And then we're also going to want this function to ask the user how many numbers are going to be in the array. So kind of how many cards are in the deck that we're going to be shuffling. And because we can't decide necessarily... we can't decide to change the length of the array that we're putting these in, we will have some kind of maximum number that we could have, and we'll have a very big array that we may only be using part of. So this is something that we do when we don't know how many of something that our user needs. We'll set ourselves an arbitrary maximum and then say, this maximum should be so big that the user's not going to need that many of them, and we'll just use the first portion of the array to do stuff. So it's kind of like... if I don't know how much someone needs, then I'll make an array I'm just trying to go quick here, that has lots of cells in it, and then my user will say, I want 4 things, and I'll be like, sure, you can have 4 things. We're going to use this, and then all the rest of this here is just going to be empty, and we're never going to use it. So all we'll need to do is if our user tells us they want 4 things, and we'll go, okay, then we know we'll keep a variable somewhere that says this is how much of this array we're going to use at any particular time. So this is one way that we're going to deal with not knowing in advance how big something needs to be. Let's say, for example, someone is, I don't know, trying to put blocks on a map in an assignment or in a game, and you don't know how many blocks in advance are going to be needed, but you know that there's a kind of a theoretical maximum. Then you could say, all right, this is where we could maybe store this information, and we could say, if you say this many things, I'm now going to loop exactly that many times and read input and do something with it. You know, you don't even need an array in that example, because you could actually just do it by reading the input, throwing it away, and then doing whatever it's asking you to do. So yeah, as usual, I will every now and then do something sneaky, which is exactly what you need for your assignment, but it's not exactly, but it's very close. Alright, let's start a new file. I'm gonna close gedit there. Shuffler. What are we doing, gedit? Are we running? That's a little weird. Did it create the file? Ooh, everything stopped. Let's try that again. Okay, I don't know what happened there, but that's okay. Okay. That takes input of a series of numbers and stores them in an array. It then shuffles the order of those numbers and prints them back out. A demo on using functions and pointers. What are we in? We're still in March. We're in March 2021. March 2021. Okay, so we're going to include our standard input output .h because I know that we're going to need to, as I said here, take input and print stuff out. I'm going to say scans input. I just like, sometimes I like to use the same words as the function names to make it easier for us to remember stuff. Someone's saying that VLab has been glitchy today. Ah, that's awkward. Hopefully it doesn't glitch while I'm trying to lecture and I've got like a time limit to finish this stuff. Okay, so I've got my main function, which you now know is a function, this main function. It is not just some magical thing, it's another function, but it happens to be the function that my computer looks for when it says, I want to start this program. So, in my main function, I'm going to create an integer array. I'll call it deck, because I'm gonna treat it like a deck of cards. And I think to begin with, I'm just gonna make it all zeros like that. But I do need to decide this here. I can't just have an array that doesn't have a particular size. So I think this is time for a constant, which is going to be like, ooh, let's lean in on the analogy of the shuffling the card deck, and let's say that I'm expecting this to be a fairly standard card deck, which would have 52 cards. So for the interest of safety, I'm going to do 100 just in case people do something strange with it. I have a big ceiling. This does mean that I'm pretty much guaranteed to waste some memory. I'm going to be assigning memory to this array here that I probably won't use. But that's okay. I'm happy with that because I know that 100 integers worth of memory is, what, 3.2 kilobits, which is about 4 kilobytes, 4,000 bytes, and so I don't really mind that much. It's not enough memory to cause problems in my 16 gigabytes of memory, or in VLab I think we get 8 gigabytes of memory per program that we run. Me using 4 kilobytes here to just have a safety buffer is fine. If I wanted a good safety buffer, I can just keep going. I can be like, this still is not going to cost enough memory to be a problem. So this is just me saying, theoretically, I don't think this program will ever be used with more than 1,000 cards. So I'm going to do this. I'm going to go for 1,024 just to be like, yeah, I can be this safe. That's fine. Okay, so if I've got those deck of cards and I want a function that's going to read in a set of cards that my user types in, I'm going to make this an integer function because one of the things that I want my program to do, I want my program to know how many cards are in the deck. And if I want to know the number of cards, then I need the function that's going to read in the user's input to tell me how many things it read in. So let's go read input. And what is this thing going to need? If I need the read input, I need to know where I'm storing it, so I need this deck. Remember that these aren't the same variable. Even though they're going to be named the same, one of them is going to be the variable inside the function, the other is going to be the variable inside the main. Having said that, they're both going to be copies of the same memory address, so that should be fine. If I want to make this really explicit and really clear what I'm doing, I might actually say that this function works with an array of exactly this size. So if I was to make more arrays, this would make it really clear for me which arrays are going to be used in this. This is going to be a deck array that goes in here, into this function. So let me copy this function, paste it here. So this is where I'm going to actually write the code for this function. Asks the user how many cards are in their deck, then reads that many cards, or max cards if it's lower. Wait. If the user says too many. Returns how many cards were read in. So this is important, right? I'm actually programming some safety into this. So if my user types in, I have 15 million cards I want to type in, my program's just going to read the first 1,024 of those, and it's going to say that's it, right? And so I have this safety thing where I'm never going to go over the length of the deck that I'm building like this. Someone said semicolon. Oh yeah, because I've just put this num cards here, but I haven't really done anything with it. I'm actually going to do this rather than the semicolon. I'm going to read input, and the thing that I'm going to give as input is the deck. So what I'm going to say is the total number of cards is actually the result of the function that read the input. So what I'm trying to do here is trying to make it so that the function reads the input, and once it reads the input, it will tell us how many things it read in. Someone's saying I should help out with the Eng1000 coding safety stream. I can't remember who's teaching Eng1000 at the moment. I'm sure that they're going to talk about that somewhere along the line. But yeah, so I'm trying to make this thing so that if my user tries to go over what my maximum capacity is, this is not going to return the number that the user told me. It's going to return the number of cards I actually read. So let's have this num cards, and it's not going to have a value yet. Let me just, sometimes I like to put a few enters here so I'm not working at the very bottom of the screen. So number of cards, then I'm going to ask my user how many cards. how many cards are in your deck? I wonder if I should put a new line here or not. Maybe I will. This is like a matter of personal preference whether you put a new line on something like this. Sometimes I like to put a colon and get the person to type in the number straight afterwards, but because I put a question mark, I did that. It's, you know, it's much of a muchness. You choose these kinds of things. There is an entire field of study about designing stuff so they work better for humans. And yes, I've done work in that, but I'm still not necessarily like a super expert on exactly the best way to make user interfaces. And we're on a command line, it's a really specific interface anyway. So we're going to scanf, and now we have more of an understanding about scanf than we used to, and we know that what I'm giving scanf is a pointer to the integer num cards. So if I say and of num cards, I'm saying what is your address? And a pointer is an address. So what I've actually done here is very, very similar. So I could do this. I'll show you something if we're going to use pointers. So I've made a pointer to num cards. This is a little bit excessive. I don't really need to do all this. But I've made a pointer to num cards called num cards pointer. And it will store the address of num cards. In my scanf, I could actually give it this pointer, because this pointer is storing this address, and so either I put and num cards in here, or I can put a pointer to the variable that I want scanf to write into. So now that we've actually learnt a little bit about pointers, you can see that this num cards pointer, because it's storing this address, could be used in its place. So a pointer and an and or something are the same kind of thing. They're one of those hexadecimal numbers that tells us where something is. I'm not going to leave it like this because this is just excessive coding that I don't need. But it's good to see, I think, that now that we've seen a bit of pointers, some of you maybe, like, this is an old story. It's really funny. I had a friend who literally did not understand how pointers worked until his second year of computer science. And that's fine. It's not the kind of concept that I expect you to be able to use just yet. It's the kind of thing that builds up over time. So anyway, we're going to scan in the number of cards there. Scan in the number of cards, then loop through the deck, writing in the numbers that the user types in. So, if I'm going to loop through, I know I've got an iterator that's going to start at 0, especially if I'm looping through an array, I'm always going to start my iterator at 0. While loop that goes until I is less than the number of cards, which is the number that the user has told me, or, oh wait, not or, I need both of these conditions to be correct to keep looping. I is not just less than the number of cards, I is also less than the maximum number of cards. So if someone gives me a number over 1024, I'm not going to try to write into an index that doesn't exist. Just looking at, yeah, people saying the different ways of doing the array. So I could have, if I wanted to, I could have said, you can take in any array for this. And then I could have had another number, which was the length of the array, and I could be using that. But this time I'm doing this a slightly different way, which also works, where instead of using the length of the array, what I'm doing is I'm using this constant that says, I already know exactly how big this array is, and I'm going to use this constant as my number. So I know that my array is size max cards, so I say either this number, if this number is smaller, that's fine, we'll stop earlier, otherwise we'll stop at max cards, so I will not allow you to try to write into an index that doesn't exist in my array. Which means there's actually a hidden maximum. The user doesn't know that there's a maximum, but we're counting on the fact that it's high enough that people wouldn't reach it. So, each time we loop through, we're going to scanf in. And I'm not going to bother asking the user for the things each time. We're just going to get them to say how many cards, and then they can just start typing in the numbers. And each time we're going to scanf, we're going to enter a number into the array. So we have deck I, because the I is the iterator that was going from 0 up until a certain amount. That's going to enter that into the array. So we do need the address of that, because if we're grabbing an individual element of the array, that's not its address. We still need the AND for the address. If we're grabbing the whole array without grabbing an individual element, then deck would have been sufficient for the address. But since we're getting an individual element, we need to say what is the address of that individual element. We'll scan in there and we'll keep looping. So we have read I cards. That's actually the same condition here. Have read I cards. Sometimes I like to put this stuff here to remind myself of what's going on. So I've read I cards, which means that this I is precisely the right number for how many cards were read into the deck, regardless of which way it stopped. If it stopped at max cards or it stopped at num cards, I will be the number that tells us what's going on, which means I can return I now. So I can say I, because I only went up whenever we read something in. I have read I cards. Now, at the moment, I am also not doing any proper checking to make sure that numbers are being entered. So if someone enters in letters or something like that, I'm going to have a problem. Don't know why my Dropbox is doing stuff right now. Anyway, yeah, so I could have a problem there, but I'm just going to let that go now because this is a basic example that I'm doing. So return I is going to say, I looped this many times and that's how many cards I read in. So now this variable, once this function finishes, it's going to put its value into this variable. So I'm going to know how many cards are in my deck here. To test whether this is working, we're going to need to be able to print out the deck. Nicholas is asking there, should we be using char at all in our assignment? No, don't worry about it, you don't need it. The assignment is entirely written on integer arrays, so you won't have to use it at all. Okay, so now we have a way of reading input, not just reading input, we know exactly how much of this array that we've actually used, because this array is massive. It's got 1,024 spaces in it. If I'm only giving 10 cards, then I'm only using the first 10 slots of that array, 10 elements. But this number will remind us how much of the array we've used. So let's do a print deck function. Just to make sure that I'm following what's in the slides. But I'm pretty sure that was the next thing. Yeah, printing out the numbers. So I want a print deck function. So in order for the print deck function to work, it needs the deck itself. So we're going to go with this explicit naming of the size of it, because we're just going to be using that to remind ourselves exactly how big it is. This doesn't really do anything. This doesn't mean that this function's not going to accept an array of a different size, because anytime a function gets input from an array, it's just a memory address. It doesn't actually have that extra information to tell you exactly how big it is. So you still need to know how much of it you're going to use, which is why we have the constant here that tells us all the way through what the maximum size is. But when we're printing out the deck, we only want to print out how much of it we've used, which is the number of cards. I'm just going to call that the length, to be a little bit similar, to remind ourselves this is the length of the array. I don't know if that got picked up in the microphone, but there's a massive storm over my house right now, and there was like thunder just booming in the sky a second ago. Okay, so here's my function here to print the deck, and I'm going to say prints out the first length elements from the deck array. I don't know why I made that an integer. Actually, were people asking that? I wonder if anyone else was asking that yet. Not necessarily, yeah. So someone could have asked at this point whether or not this needed to give back an integer, because if it's just printing stuff out, it doesn't actually need an output. So I'm actually switching this over to a void, because it's just a print out thing, so I don't think I need any information back. We'll see. Sometimes as I go through and I start using things, I go, actually, I needed some information back. But hopefully this won't need anything. So in order to print out an array, I'm going to need to loop through the array. So I'm going to do my bog standard thing here, which is just to set up my while loop before I put anything in it. And I'm going to say that I was going to print out the first length elements. So I'm going to say that this is my limiting factor. So if I is less than length, then that is the stuff that's going to get printed out. And I'm hoping that this will never be used incorrectly. So I've made an assumption that this length is never higher than max cards. I'm reasonably safe in that assumption because I know that this thing that created that length, that number of cards there, was maxed out at max cards anyway. So hopefully I'm going to be okay, but I just want to be like, you know, a little bit... I'll just have to remember that, I guess. That's an assumption that I made. So, I is less than length. We're going to be looping through, and every iteration we're going to loop through, we're going to print out. So we're going to print out a number. So I might just do these in a row. So a number and a space. Let's be nice. Number and a comma and a space. So it would be really clear to see the difference between these. And the actual number I'm printing out is one of the elements of the deck. And I is the iterator. We're starting at 0, going through the deck. So it's going to be I. Like that. I think that's going to be enough. Oh, you know what? I might put a safety in here, just because, like, sometimes when I say I made an assumption about something, I want to, like, let's be 100% sure about it. Okay, now I can't be screwed up. No one can put a number in here that's too high, because I'm going to stop either at length or max cards. Because it's an and, I'll stop at whichever one I hit first. So this should print out my deck. Let us now... Oops. Oh, yeah, no, we're here. Print deck of the deck that we've created. So now we can test this, and we can say, okay, is our input working? Here is my read input function working, and is my print deck function working? So let's save this, compile it, and run it. So this is something that I'll do a lot, and I've tried to make this kind of reasonably... a little bit like this for you in your assignments, where instead of asking you to do the final project with everything in it, I ask you instead to do this small part of it, and then another part of it, and another part of it, and they add up together. So in the same way that I'm not even shuffling anything yet, I'm not even thinking about shuffling anything yet, but I do need to test these two functions to make sure that they're working before I go on and do other things. Okay. Oh, we haven't compiled this at all. So I'm just using my tab complete there, makes things quicker for me. So I'm going to compile it to the name shuffler. Uh-oh. Error. Too few arguments in the function call. Expected to have 1. Did anyone notice that? Oh, there was no... He's behind you. Okay, so print deck as my main function knew, because it said print deck took in the deck, and also needed to know how many cards you wanted to print out. So I actually wanted to print out this number of cards, because that's how many cards I read in. Num cards. Okay, let's see how this works now. It's in front of me. Yeah, I saw it. That's very, very rare that I will see something before any students will see something. Because usually if I've written it, I've already made the mistake. So I usually won't go back and see it. Okay, let's run the shuffler now and see how it works. How many cards are in my deck? Let's keep it simple for ourselves for the moment and just put 5 cards in the deck. 1, 2, 3, 4, 5. Scanf is going to ignore the spaces in between these things. So when I press enter, the scanf will probably loop through and run 5 times. And it prints the deck back out, 1, 2, 3, 4, 5. We've got a comma in the last one, which is a bit fiddly, and no new line at the end of that function. So maybe I'm going to clean up that a little bit. But at least I know it's working. I know my reading in is working and my printed out is working, because this obviously went into an array somewhere and was printed out as the same set of numbers. So that's good. I like that. Just going to neaten this up with a new line. I won't bother making the final one not have a comma, because that's just extra fiddly code that I don't really need to do in this case. Okay, so I know that my my read input and my print deck are working. So the next thing that we're going to do is have the function that swaps variables. I'm going to go easy on myself here. And, oh, hang on. Copy pasting code. Look, I wrote the code, so I can copy paste it. The swap code is reasonably well understood, and you've seen it. I've talked about it already, so I'm not going to necessarily type this one in. Swaps the integers at the destinations of the pointers num1 and num2. Now, for my main to know this, I need to copy this and put it up here. So what I'm going to have now is, if I have the address of one number and the address of another number, this thing is going to go into those memory locations and pull stuff out of one and shift them across and swap them over. So this doesn't even know what's at the end of these things. So it doesn't know whether these are part of an array or anything like that. It just knows that it's expecting integers at the other end. It's going to do something to them. So I can actually give the swap information from my deck here. So let's test this swap function now by saying swap nums, and it wants 2 pointers, which means it wants 2 integer pointers, which means it wants 2 addresses of integers. So I can give it 2 addresses of integers. So let me say deck 0, and it wants the address of that integer, so that's the address of deck 0 and the address of deck 1. So what I'm saying is, can you just swap the first 2 elements? So if this is just going to swap the first 2 elements, then we should be able to test this, and we should be able to put a deck in, and we should see the first 2 elements get swapped by this before it gets printed out, and then we'll be able to see whether the swap function is working or not. Especially because I just copy pasted this. I mean, I tend to trust the person that wrote those slides because it's me, but it's still past me, so I'm still going to test it. And I think that this is working because I've got a temporary integer that I copied from 1 into, and because I've saved 1 in there, I can copy 2 over 1, which is fine, and then I can copy the temporary over the 2. So I think this is going to work, but let's run it and make sure. Actually, I should just use my up and down keys. There's my shuffler, and I'm going to run it. Let's just do 4 cards in the deck. I'm going to do 2, 4. I'll show you like interesting things that scanf can do. It's ignoring the white space. It's just using any white space and the enter key and stuff like that to separate the numbers. So I've got these on separate lines. Because this scanf is just grabbing one number at a time, it's actually quite happy to do this. It's just going to ignore the enter key that I put in between. So I said 2, 4, 6, 8. And we had 2, 4, 6, 8 in the array, and then we swapped the first 2, so we end up with 4, 2, 6, 8. So I'm happy there. That seems to be at least swapping one number like that. Oh, Lorenzo is asking, what happens if you point to an array with more or fewer elements than the number in the function definition? So if we had a different deck than this one, so we want to see if these functions will still work. Let's try it. Okay, so I'm just going to do a size 10 deck, but I still have this weird max cards 1024, which means we could potentially have big problems when we try to run these things. But let's just see if the functions will allow it. If not, so I'm going to compile, it will compile, and it's running. So this is safe only if I use something less than size 10. Once I go over size 10, this thing thought that, these functions thought that the size of the deck was 1024. But this is actually going to work now. So if I do 1, 2, 3, it's going to swap the first 2. So this, me putting the size of the deck in the functions, was actually very much for a human thing. That was us to remind us what we expected things to be so that we can write these functions with this expectation. The computer is actually going to take this whole thing as an integer array as just a memory address for the start of the array. So it's actually, I could put a pointer in this without any idea of what our array was aimed at. Anyway, let's do the final. Oh, let's fix this, because that's very dangerous right now. I'll put that back the way that I wanted it. I don't know if that showed up on camera, but the lightning just hit outside my window. There. Okay, so let's do something that swaps multiple numbers, and it's a pretty massive storm. That swaps multiple numbers rather than just one, so we get this shuffling thing happening. So I'm going to do another function here. Oh no. Oh no. Is my stream still going? My stream is still going, so my internet connection hasn't blown up. I'm a little afraid for my computer at the moment, actually, but I pressed enter then, and nothing happened in VLab, which might mean that UNSW currently has connection issues. We'll see. If this storm cuts off everything that I'm doing... Oh, no, we're okay. We're okay. I'm a little afraid right now. This is usually, like, if I see lightning hitting outside my window, it's not necessarily the time that I would leave my computer running and connected to the power and the internet, but, you know, we've got 10 minutes left. I should try to finish this lecture. The most expensive lecture I ever did. I blew up my computer. Okay, so we've got a deck of cards that has a theoretical maximum of max cards, and we have a length which is how much of this that we've actually used. And what we're going to do now is we're going to call the swap nums function multiple times inside the shuffle function with different pairs, swapping these different things around, and hopefully what that will do then is kind of shuffle our deck, pseudo-randomize our deck. It's not really going to fully randomize it. Okay, so I'm going to call swap multiple times. This is the function where I issue the challenge to you. Can you write this function so that it does more shuffling than mine? Because I'm going to do a really simple shuffle where I'm just going to loop through. I is less than length. Just set up my while loop. And for every card in the deck, I'm going to swap it with some other card in the deck, and then we'll see how we go like that. There are probably lots of different ways to write this function. So I'll leave it with you if you want to play around with it, but I'm just going to do a simple one, which should do enough swapping. So what I'm going to do is create another integer, which will be a different index into the array. Often when we're doing two loops, we'll use a j as the second one, so maybe I will use a j here, and I'm going to set j up as equal to... What's something that we could do? This'll do a weird swap, so maybe this will work. J is equal to I times 3. The only issue with I times 3 is that we could very, very easily push this off the end of the array and it'll be out of bounds. So if I wanted to bring it back into the bounds, I'll do I times 3 mod length. My spacing is horrible here. Now it's more readable, yeah. So I should put a comment here because this is a random piece of code. Find another index pseudo-randomly. It's not even remotely randomly, but I'm just grabbing another index here. So this is the kind of thing where you write a line of code like this that has basically no meaning. You do want to explain it. So this is me just saying, just grab another card from the deck. I don't really know how this is going to work. It's going to work differently depending on how many cards are in the deck. So maybe it'll do something, and it's going to start swapping those cards. So, the first one it's not even going to swap, but the second one, which is index 1, is going to swap with index 3. Then index 2 is going to swap with index 6, and depending on if we go off the end of it, they'll start swapping random things. And Jack, pseudo is doing heavy lifting in that comment. It's not even remotely random. You know what? I'm going to take out the word random, because it's really not. Find another index to swap with. Yeah, so this is our other one that we're going to swap with, and then we're going to call the swap nums function. So the swap nums function is just going to take the values and swap them around. And swap nums wanted to know pointers to two different numbers. So pointers being memory addresses, I'll give it 2 memory addresses. So I'm just putting my my ands in here to remind myself that both of these are memory addresses, and they're going to be memory addresses of 2 elements of the array. So this is dec I is one element of the array, and dec j is the other element of the array. So I can do that. There's actually interesting other ways to do this. So if I'd made swap nums not take pointers, and instead take an array and 2 indexes, that also could have worked. We could have done this a different way, but I did want to use a function that had pointers in it. So I'm giving it the address of 2 cards in the deck and saying swap these 2 cards in the deck. So someone was asking about the length. The length comes from this, in my main here, this number of cards, which comes from reading the input, and reading the input was here, how many cards are in your deck. So the length is given by the user the first time they give us the deck of cards. So now I'm not swapping. Let me make sure that's actually everything this thing needs to do. I think that is everything this thing needs to do. It's going to loop through, and it's just going to swap some pairs. So it doesn't have any kind of effect that it gives back on its own. It just knows that this function, this array that was given to it was a memory address, because if we give an array to a function, we get a memory address. This thing's going to go into that memory and just start swapping these numbers. Right. So now we're going to do the shuffle. And so we're not going to swap just the first 2 cards in the deck now. We're going to shuffle the whole deck, and we're going to look. If I want to call the shuffle function, I need to see what it takes. It takes in a deck, and we have... I just said it takes in a duck. It takes in a deck. That's better than other ways I could have slipped up there. It takes in a deck, and how many cards we have in the deck, which is the number of cards here. And this is going to do the shuffle and then print out the deck. So let's save this, compile it, and run it, and see if it's doing any shuffling for us. So let's go back to the 5-card deck. And so there's 5 cards in the deck, and I'm just going to do 1, 2, 3, 4, 5. So we say that when we were given the deck in the first place, it was in order. And then when we shuffle it, hopefully this will be swapped around a bit, so it won't necessarily be in order. So let's see if it worked. Ah, nice. 1, 3, 2, 5, 4. That is in some way having the deck shuffled so that some of the elements are not in the same place as before. It's not a perfect shuffle. One of them still stayed where it was, but you know, that's not that bad. A lot of these have moved around, so we have in some way shuffled this deck. Lorenzo's asking, does addressing and dereferencing cancel out? Can you do star and variable? You can do and star variable. So you could do something like this. So I could have num cards. I could have what is the address of num cards. That'll give me an address, and I can dereference that address. So this should take me back to num cards. So you can if you want to. It's a bit fiddly, but you can. It's also completely unnecessary, but it's possible. Okay, so let's have a look at this program now. Because what I have done with this program is something that I love. This is something I love doing with programs. This is my program. This is my main. So my main function says, make a deck of cards, set the number of cards to be reading the input of the deck, shuffle the deck, print the deck. I have created a program that is so readable that someone that doesn't know how to write C will be able to read this and probably tell me exactly what it does. Because I've got a deck with a maximum amount of cards in it. This is the only line that's confusing. Because if you don't know what the output is of read deck, then you don't really necessarily know. But we're talking about reading input, and we're talking about shuffling and then printing. That's it, you know? So, when you're reading this code, look at this. I didn't put any comments in my main, because I don't need them. This is written in such a way that you can just look at this and go, I know exactly what's going on here. You can not know C, and you can have a good crack at what's going on here. So this is for me. This is this is the holy grail of main functions. And then anywhere you want to look at the details, you go, okay, let me look at what this function does because I want to know how it stores that number. I read this. So even here, I'm not having to skip over this code and find out what it does. I have a comment specifically here that says what this function did. And I want to look at this function. I've got a comment that says what this function does. I've got a comment that says what this one does, etc. So even at the second level where I go in for more detail, everything is fully explained. And then only if I want to go, okay, exactly what's happening then, do I go in and look at the code and stuff like that. So this is anyone wants to get like full style marks in assignment 1, this is like a prototype of how to do that. Also, people looking at assignment 1, there's something you just, even in stage 1 of assignment 1 that says, how many things would you like to input? And then loops through grabbing that input. Oh, look at that we did here. How many things do you want to input? And then we looped through and took the input. It's not exactly the same. I'm not going to do your assignment for you. It's not exactly the same, but this idea of this function might work pretty well for the setting up of the map in Slide. John Fangling, copy paste mode on. This is one of the places where you can copy paste. I mean, but I have set this up intentionally where if you copy paste this, it won't work. So you still need to do more work than that. But we've hit 6 p.m, so I will wrap it up there. And I'm happy with that because I've wrapped up exactly the program I wanted to write and I wanted to show you. So I'll go into break mode now, and I'll come back in a second. And if anyone has any questions and wants to look closer at what's going on here or ask more details or anything like that, I'll answer your questions after a short break. Alright, I'm back. Did anyone... Oh, thank you all. Thank you for the thank yous. I think someone was asking Jackson. Oh, Jack has already answered. The revision tests are not marked. I mean, they're marked, but they don't have marks, if that makes sense. As in, like, you can submit them and it'll tell you how well you went, but it's not worth marks in the course. They're just valuable for your exam study and stuff like that. Lorenzo is asking, what is the link between pointers and arrays? Lorenzo, don't ever be worried about asking questions. So many times when people are asking questions, they get embarrassed about asking too many questions. What you're usually doing is you're getting embarrassed on behalf of other people, which is actually just really nice. So you're asking questions that maybe other people are scared of asking. So no problem if you think, oh, I'm not sure if I definitely need to ask this, especially now. Like during the lecture, yeah, I might not answer because as you see, I end right on the dot. So thanks for coming, Jack. See you soon. Yeah, so when I'm ending right on the dot, you know that means that like I'm rushing to make sure I get exactly the content out that I want in the lecture. But after the lecture now, happy to answer your questions for sure. And yeah, and a lot of the time your questions are going to be really valuable to other people. So the link between pointers and arrays, I think the most interesting thing about pointers and arrays is arrays are a way of using memory that has addressing for individual elements in the array. Funnily enough, memory is exactly the same thing. It's just a sequence of storage where you can address individual parts of it by their memory address. Those hexadecimal memory addresses might as well be array indexes, because if your entire memory in your computer is an array, those indexes are literally the numbers. They're just split up into different size chunks. An array is split up into chunks based on the variable type it has. Memory is always split up into its minimum sizes, but the addresses are the same, because every variable is always going to be a multiple of the minimum size. So every variable is going to be a certain number of bytes. So your integers are 4 bytes, your doubles are 8 bytes, and your arrays are always a multiple of those sizes. And every memory location is 1 byte, which means if I grab an integer, I get four memory addresses, basically. Only the first one really counts, but I'm using up the others with the 32 bits of information. So the array, when it gets passed into a function, or even just if it gets used without the square brackets, so when I use the dec without the square brackets, what it is there is actually the address of the start of the array. If I use the square brackets, it's nearly like me using a pointer and dereferencing it. I'm following that address in, and then I'm jumping over a few addresses to get to whichever element that I'm looking at. So you can really think that, like, if you want to boil it down, an array and a pointer are just two different notations for exactly the same thing. They're two different notations for memory addresses. The array has a little bit more information attached, which says, I'm a memory address, and also I am an accessor for a specific amount. I gotta watch where my camera is. A specific amount of that memory in these size chunks. So it's just more information on top of a pointer. But functionally, when it goes into something like a function, it acts very similarly to a pointer. You can even do funny things with pointers. You can put square brackets after pointers and start going into them. And then if that isn't a pointer to an array, everything blows up immediately. But if it is, it actually works. Okay, any other questions? Alan is asking, do only int functions need returns? Yeah. So the void functions don't need to return because they just finish on their curly bracket. You can return in them. I can do this if I want to. But it's kind of superfluous, right? Because it was going to end there anyway. So me putting return doesn't actually really change anything in a void function. It's legal C, but we don't do it because it's unnecessary, because the void function is going to run till its end. When we want to give back something is when it makes sense to use the return keyword. So it's like, if this has a value it needs to give back, and it has an integer value here that I want to give back, then we use the return keyword. Alan's asking, have I put the code up for Shuffle yet? I apologize, because usually I actually give you the link, and I forgot today. So here's the link, and I'll copy this and put it in chat there in case you need it. Having said that, the link was also in the lecture section on WebCMS, where you got the link to be in this stream. So probably just remember you can always access it there in case you need it. But in case you can't see it, that's the link there. And I copied it into the YouTube chat there. Marcus said, okay, my brain hurts after 8 hours of continuous courses. You're going to have to rewatch later. Yeah, okay. I understand. 4 to 6 p.m. on a Friday is not the best time for human brains. So hopefully your brain will be happier later, and when you go back and watch this, it works for you. Autumnal Blake is asking, is a character 1 byte in C? So we're jumping ahead. Actually, I think we're going to be looking at those next week, but yes, it is. So the smallest size thing that we can use in C is actually a letter, rather than a number. Mal is asking, does that mean there's no need to use star array? Yeah, if you use a star on an array, you should try it out, actually. Because it's quite interesting. So let me show you, just while I've got this here. I could do a printf on a number and do this. So star on the array is going to dereference the array. Dereference is follow a memory address to its location and read the value there, which means this is going to follow the deck memory address to wherever this thing was first created, and it's going to then read the value there, because that's what the star is going to do. So what that's going to do is actually, if I hope this works, but I'm pretty sure this is going to work, it's going to read the first value in the deck. So let's run this and see if it actually does that. Wait, we have to save that. Oh no. Compile this and run this, and what it should do is it should do everything it was doing normally, like it will shuffle the deck and print it out. But then it's going to reprint the first element of the deck. So let's see if it does that. This will do exactly the same shuffle, I think. 1 2 1 3 2 5 4, and then it's printing out 1. So yeah, it's doing that. So you can, anything that's a memory address can be dereferenced, but you do have to be careful of what type it is when you're dereferencing it. Usually this deck will know, because it was declared as an integer, it'll know that it's basically an integer pointer, so I can use it as an integer like that. So it's interesting, right? Because any memory address anywhere is probably aimed at a variable. So anything that is a memory address as a pointer, as the name of the array is a memory address, you can dereference any of those. Okay, so that was Mal's question. Lorenzo, if we define an array as int array size 10 equals empty, that will make an array of size 10 that's all zeros, then variable array is a pointer to the beginning. Yes, an array square brackets x is like dereferencing, exactly, Lorenzo. So the square brackets says I'm going to dereference, but it's a very particular form of dereferencing, because it says I'm going to dereference a memory location that there's this number of variables after the memory location that I've been given. So, for example, this deck 3, this dereferences the piece of memory 3 integers in after deck's memory address. So it goes, this is an integer array, so 3 means I am 3 integers in, which is 3 times 4 bytes, so 12 bytes in after this address. That is the thing that we will read, and because it's an integer pointer, we'll read 32 bits of memory, 3 integers in after that memory address, because the array in memory is 1 piece of memory. So that's what this thing will do. So yeah, you're starting to get the idea. I always like this part of the course because it's kind of like we've been using these things, and people are like, oh, I just use this array. It's just this thing, and then I go, oh, arrays are actually a piece of memory, and every piece of memory has an address, and every element within the array also has an address, but they're all very related to each other because we know that arrays are always a single chunk of memory. Arrays are never separated into parts. So that's how we can use this kind of jumping around. And underneath it, C is actually doing this kind of address jumping around. So Alex is saying, it is fine if I don't add the AND for the shuffle function. Shuffle function here, let's look at where the ANDs are in the shuffle function. Probably these, right? So if we did swap numbers like this, there would be some issues, right? Because here we're taking values from numbers in the deck, but swap nums is expecting addresses, not just the number values. So we're going to give it like 1, 2, 3, 4, and 5. But it's expecting 0xFFCCA, that kind of stuff. And if we don't give it the proper locations, it won't know what to do with them. So we do need the ands here to have the proper locations, because what we've actually done here is we said, yes, this is a memory address, but this has turned it back into a variable. So we've gone to an individual variable somewhere after that memory address. And then we've said, now that we found the variable, find the address of that variable. So we're doing this kind of double thing here. So we're not even using the fact that this was initially a memory address. If we wanted to, I guess if we wanted to, this is like super, super, super dangerous coding, and I never suggest you do this. We could have done this. This is like theoretically possible. Dec plus I times 32. Wait, no, it's not 32, it's bytes. I times 4, and dec plus j times 4. Don't ever do this. I'm just doing this to explain that this is theoretically possible, but if you run this on a compiler, on a different compiler in a different kind of place and time where integers are not 32 bits. So let's say we cross over into a future world where we go, we've got so much memory in our computers now, we're going to use 64-bit integers all the time instead of 32-bit integers. Then this code breaks. And you're like, oh, why did that code break? It was like fine, it ran for years and never had any problems. It's because this is working on a really strict assumption that integers are a certain size, whereas this isn't. This is just going to allow the compiler to move us to different memory locations. So yeah, technically we can do it without the AND, because this is a memory address, and we can, because a memory address is a number, we can fiddle around with that number. But this is super, super dangerous. This is nearly like, it was nearly thinking about not even typing that in, because it's so dangerous to use. Okay. So Schrödinger's, I spent the whole lecture showing in Mark's coding for more efficient method for practical learning. Don't know if it worked. I'm not wearing it today. Last lecture, actually the live stream yesterday, I was actually wearing a Naruto t-shirt. Sharingan is Sasuke's power, right? In Naruto? Do I have that right? It's been a long time since I watched it. So yeah, you were practicing and changing some of the stuff that I was doing, which is cool. I think that's like one of the things that's interesting is you can take what I've done and you can go, oh, there's actually more in this program than what Mark was doing, so there could be more interesting stuff. Mohammed Hussein is saying, how are functions being called from the main function? So when we call functions, what we do is we call them by name. And you know how we were talking about different symbols meaning different things? You know a function's being called when you see these brackets. So pretty much, yeah, and I think all functions are always going to have the brackets after their name. So their name and their brackets, and then inside the brackets are whatever information we're giving to the function. Some functions don't even have anything. Some functions are empty here. But these ones that we're using here all have it. So when we go through our code and we see this, and we have the brackets, that means that we're putting some information into this function. So when this happens, my computer is going to jump to wherever it finds that name down here, and then it will create this variable and it will go through line by line and run this. And when it's finished here, it will jump back to here. So this is something that's kind of like, it's like an agreement between us and the compiler that when we say this, what we mean to the compiler is going to say, okay, this is a point at which the person leaves the main function. So they're not going line by line through the main function. They're going to leave the main function to the thing with the same name. And then they're going to go through this until this thing hits a return or its close brackets. And then we're going to come back to here. Because this was an integer function, this thing evaluates to an integer. So when it finishes running, it becomes this integer. Which in this thing is going to be an I. So it'll take the value, the last value that I had there, and it will pass that back. And so this thing will transform into the last value of I, which we can then use and store in this other integer there. So hopefully that gives you a little bit of like, this is how functions are actually working. They're jumping around in our code in a way that we didn't before. We used to just go line by line. Blake is asking about the assignment. I think check whether there's details in the assignment, but I think there aren't. I think on purpose there aren't details in the assignment, which means on purpose I'm not going to answer your question there. But one thing we have done is that the reference solution for the assignment will have all of the information in it, but you need to actually know how to test the reference solution to dig the information that you need out of it. So that's the clue I'm going to give you, Blake, for that one. So Lorenzo is saying dereferencing deck is the same as dereferencing the first element of deck. Yeah, so I think you were talking then about that example I did earlier where we looked at the first element. I should probably delete this because this is not legal code and it will break my example. Alan's saying, can I just think main is the whole body of a program and we put organs into the main and after that we define what those different organs are? I've never heard anyone say it like that, but yeah, you can think of it like that if you want to. You can think of like, this is the body and inside these body are these other parts. And we name the parts, but we don't describe them fully, like there's a heart. And then if you want to know what the heart does, you have to go into the detail in it, and it goes, okay, it has electrical signals that go through, and the electrical signals make these muscles pump at different times, and it has these valves that do this thing, and so here's the detail. But if you don't need to know that detail, you just go, oh, it's just a heart, So I think that's an interesting way of thinking about it. That's a nice one, Alan. So Ayub is saying, hey, you see with the shuffler code, we swapped the elements of the array using a void function. But don't we need the new information of the reassigned elements, so it shouldn't be void? Well, interesting. So think about what I gave to this void function. I gave this thing a variable, which is an array, and that array variable is the address in memory of an array. And so when I call it in the main, I gave it the deck, and the deck of cards here is something that is actually a memory address that is inside my main. So it's one of the variables that is in the memory space that my main function has. So my shuffle thing is actually accessing memory that's in my main because I gave it a memory address of it. So when I give swap nums memory locations that are related to this memory location, this is all working on this piece of memory, because that's the only piece of memory that's been created there. When I give an array to a function, I'm giving a copy of the array's address, so a copy of the location where the array is, and then anything I do to it is actually going to be working on that original piece of memory. So hopefully that helps. So that's the stuff that I was kind of talking about earlier. This might be worth a second watching to see what I meant when I was talking earlier about the difference between pointers and arrays, or even what is the similarities between pointers and arrays. That might help there. Lorenzo's is like, is this why we count from 0? Yes, it is. So I think that's you reacting to when I did the multiply that by the amount of memory passed. So the address of the first element in the array is the same as the address of the array. So that's why we dereference that. Well, not dereference, that's why we index that with 0 to say don't change where we are. 0 says no change, and 1 says go 1 further in. That's why 1 gets you to the second element. I love how your brain exploded on that. It's like, yeah, totally. Yeah. So that multiplying addressing thing that I did was all about moving through memory. And so if I've given you the address of the first element of the array already, and then I say square bracket 0, I'm saying don't move through memory. You're already at the place where you're going to read the first element. So this is all like, like the original thing was like, why is Mark starting all these while loops at 0? Like, I actually was quite polite in the beginning, and I started some of the while loops at 1 for the dice things, but after that, everything was like, while loops all start at 0, and everyone's like, Why are you counting from 0? This is like this weird computer science person thing where they've got to be like special and different, and then like, they have to count from 0. It's like, no, we're doing it because everywhere we're going to be using these things is really going to be 0 indexed things, all based on the fact that they're memory structures. Yeah. So hopefully that's all coming together. Saya Schrödinger is saying the way variables assigned across multiple functions seems kind of disorienting. I'm not sure exactly what you're meaning there, but it could be the way that I was like having functions there and these are pointers, whereas I actually didn't need to do this with pointers. I could have just given the deck to this thing and had it swap, or I could have done the swaps here. Actually, no, it's better to have that code outside. Yeah. Actually, no. This code here could have just gone in here, and we wouldn't have needed a separate function. But I also did want to show today that we can have a function that calls another function. So this function calls this function, and the main calls this function. So we're actually at an extra level of depth of functions. You can kind of see, as you go through this particular example, how it's a little contrived. I've done things in a really specific way just to show the example, whereas if I was trying to code efficiently, this function might not exist, and it might just be in here, and other little things like that. But then I wouldn't have had a pointers function to show you. Alex was doing something and it didn't compile. I'm not sure which bit of it we were talking about that didn't compile. Oh, yeah, that was you trying to take the ands off the shuffle function. Yeah, and that's like trying to take these numbers and use them as memory addresses, and these are really clearly not memory addresses. Even though they exist, they're just going to be the first few memory addresses right at the start of my RAM. Usually they're already used for stuff like the operating system. But they're definitely not the addresses of the variables that we're looking for. Lorenzo was saying, is the stream like a minute behind the chat? It's probably a lot further behind than that. I'm like 8 minutes behind chat at the moment because I'm going through and trying to answer everything. Alan's saying, what's the function that sum integers inside a bracket? I'm not sure exactly what you're asking there. You may have to clarify for me. Give me a line number or something to explain a particular function or something. Marcus is asking, what does deck mean in read input deck? So, read input takes as its input a deck of cards. I created the deck of cards, which is an array, and then I said, read input, here you go, here's the deck of cards. And it is going to be able to fit with this variable type. So when we're declaring the function, we have to be really, really clear about what it is. I'm saying that this thing that I'm going to call deck inside read input, it's not the same as this one, but it is going to be square brackets, means it's going to be an array. I left this thing in here as a really human thing to say it's going to be exactly this size. I want it to be this size, and it's an array of integers that's exactly this size. So in order for read input to run, it needs to be able to give, and to be given, an array of integers. And so here I have an array of integers, this variable that I've created, array of integers. Its name is deck. So in order to give the entire array to the function, I give it by name. A lot of people get confused here and they think that, like, shouldn't we, if we're working with an array, put the square brackets on it? But if I put square brackets on this, I'm not actually working with an array anymore. This is me saying I want an individual element from this array. If I want the whole array, if I want to give the whole array, then I just give it by its name, like that. Hopefully that explains that a little bit more. Saya Schrödinger is asking, any tips for naming variables inside the prototype functions and the variables in the functions that's in the mains? So this is always an issue where very often we give it exactly the same name if it's the same thing that's going to get passed around. But you note that I didn't do that for these. So this is the number of cards that are in this program. But every time we print deck, what I wanted to be clear on is I'm printing this first amount of cards, so it was kind of a length of how much of the array has been used. So sometimes the function has a slightly different view on the world, like it has a different view of the context of the program than the main function does. So sometimes the names will be different. I could have totally gotten away with calling this num cards though, because this entire program was based on running functions on one piece of memory, just this one piece of memory. So I could have just said all of the variable names of what goes into the functions and what they get used as inside the functions are the same. These would have to be different because these are variables that never had names. They only had indexes, so these are always going to have some kind of name. I could have called these card 1 and card 2 actually. That may have been a little bit nicer. But I think that if you follow the universal rules of things, it won't matter too much whether these are the same names or different names. So the universal rules I have for these things are, does it identify what the purpose is for the variable, and also does it distinguish it from other variables? And here we have so few variables that we can get away with naming them. When you're doing something like your assignments, you have so many variables that you have to start thinking carefully about making sure they're distinguished from each other. Blake is asking, does dereferencing mean getting the value from the address of a pointer? It means following the pointer to its address. So taking the address and following it to the location that address is telling us we can go to, and then reading whatever is in the variable that it finds at that address. So that is how I would explain what dereferencing a pointer is, what putting the star in front of this pointer, for example, is. So the star says, sometimes I like to call the star Google Maps, because it's like, this star will navigate you to your location. So you have this thing, which is an address. The star says, go to that location and look at what's there. So that's the way I like to think of it. So Sai Schrödinger is asking, just so you're paraphrasing and understanding it, return I is basically returning the number of cards, turns num cards into max cards. It doesn't necessarily turn into max cards. It'll only, here, returning I will return how many cards you've read. That's why I put these comments in here. Because every time you loop through, I tells you how many cards have been read. And you'll stop either at the number that the person told you. So these things, you have 5 and you stop at 5. Or if that number is too high and this never gets reached, like this condition for stopping the loop doesn't happen, we can use this condition for stopping the loop instead, which is to say that if you tried to go beyond the size of the array, you have to stop, right? And so I will be either one of these numbers, but it will actually be whichever of these is lower. So whichever of these the while loop stopped on is the thing that will get returned. So this is my way of saying, I'm not just going to return the number that the person input. I'm not just returning num cards, because there is a chance, however slim, there's a chance that the user tried to put in too many cards, and so we had to stop at max cards instead. So whichever one of those it's going to be, I is definitely, as the loop iterator, is definitely going to tell me how many times I went through the loop, and assuming that this worked correctly and read a number in each time, then that's going to tell me exactly how many cards were read into my deck. Which is why I is the thing I return. I don't return max cards or num cards, because it could be either of them, and I is the one that will decide between them. Right, so hopefully that answers your question there. The Ron James is it possible to use the pointers to get the values of variables from other programs, like a hacker man? Technically possible, but it depends on your operating system. Most operating systems are not going to allow you to poke into other programs' memory. Older operating systems, you totally could do that. So you could actually do things where you run off the end of an array, and if you keep going off the end of the array, you'd leave your program and go into other programs. And so that was like a, what do they call it? Is that a stack insertion hack? Where you leave your stack and then you go into a different running program stack and you actually put code into theirs. So you overwrite part of their code with your code, And when that program reaches that code, you can run something that can, like, I don't know, take over the computer or things like that, or run stuff with the other program's permissions. So if you could find your way into the code that was currently running, that was doing the password protection on things, you could then get access to things in different ways. So it's an old school hacker thing. So yeah, technically you could, but this is hacking from a very, very long time ago, and those kinds of holes that are this easy to see, this kind of idea that we could see a hole in a program this easily just by us talking about memory and stuff like that, those holes have been plugged years and years ago. But they did used to exist. So Lorenzo's asking, wait, so wouldn't putting int array max cards in the function parameter refer to the value of max cards element in the array? Not necessarily, because remember, at this point of the function, we are creating this variable. So this is us saying that this function will create this variable when it starts. So remember, the square brackets upon creation of an array say how big the array is, and you always know its creation because it has a type in front of it. If it did not have a type in front of it, and it was just this without the int, then it would be trying to access an element of the array, and that would definitely break, because the index of the size is always off the end of the array. So you note, when we're giving it to the function after it has been created, there's no square brackets at all. We're just giving it the whole array. But if we're creating something, it has both the type and the size. So yeah, so we're not necessarily trying to find the last +1 element in the array. Yep, a couple more things Lorenzo's asking, because yeah, we are running out of time. I should head off soon. For read input, could we give the address of the first element instead of dec, since they reference the same place in memory? Yes. So long as you gave a pointer or a memory address to the beginning of this array, read input will be able to do its thing with the beginning of the array. So as long as you've given it the memory address of where the array starts, it will be able to do its things. So it'll even be able to do all this square bracket stuff, and it will be fine. The only thing that we have to be careful of is that we have, well, it was just why we left this message for ourselves here. We have said that this is going to be this size, and we have a limit here. So if we accidentally give it a pointer to an array that wasn't the same size, then we'd have problems. And the other question was, code in the slides has int main, argc, argv. Ooh, oops. Where is my main? Yeah, it's not supposed to. Sorry. I'm going to teach you that later. That is the thing that we call command line input, where you can actually type in the program's name and some stuff afterwards, and it gets read in. I think that was left over because I have done things, I've changed the order of things, and so that thing I used to teach before this one, but this one now comes before that one, so I shouldn't have had that. So thank you for catching that. I actually had slides at the end here that I could have talked about, but I didn't need to. Okay, so that's the end of the questions there, and I stayed a little bit long today, so I'm happy to just let that go there. Thank you all, and good luck for any assignment work that you're doing at the moment, and I'll see you next Wednesday for a continuation of COMP1511.